Canlı The goal of the El Niño Rapid Response Experiment is to look at how changes in the weather patterns, the evaporation of moisture in the tropics, how that has changed during a major El Niño event like the current one out there, and then to look at how those changes further impact the weather on the west coast of the United States. My name is Gary Wick. I'm a physicist with the NOAA Earth System Research Laboratory Physical Sciences Division in Boulder, and I'm on assignment to the Unmanned Aircraft Systems program within NOAA.
Boy, that was the easiest we ever did it.
During this campaign, we have 4 instruments on board the Global Hawk aircraft. The first is a dropson system, which it deploys these very small sensors, much like weather balloons that go up, but these go down. So these small sensors, they're about the size of a paper towel roll, and as they fall, they collect very high resolution, vertical resolution measurements of temperature, humidity, and wind speed. So they give us a very detailed picture of the atmosphere.
Ready, Mike? Yeah.
In addition to that, we have the Hamster, which is a microwave sounding instrument, and that provides sampling much like one of the weather satellites that is used extensively in our weather models. The third instrument is HIRAP. It's a Doppler precipitation radar. So just like the weather radars on the ground, we're flying a radar on the aircraft which gives 3-dimensional coverage of precipitation, of rain droplets, and with information from those rain droplets, we can derive continuous measurements of the wind speed in the atmosphere. The final instrument is the NOAA ozone sensor, which provides measurements of ozone concentration at the flight level of the Global Hawk. The Global Hawk provides amazing capability for this experiment just in its ability to be airborne for up to 24 hours or more. That by being aloft for that long, we can sample a large range of the ocean, almost like a satellite does. That with the Global Hawk, we get very detailed sampling like an aircraft, but with the endurance that a satellite would give us. So we're able to sample this large area and look at changes in the atmosphere that wouldn't be possible with other traditional manned aircraft.
My name is John Newhouse. I'm a Deputy Project Manager for the NASA Global Hawk program. I'm actually a commissioned officer with the NOAA Commission Corps. I've been flying the Global Hawk here at NASA for 4 years.
It tastes like
as an aircraft commander and instructor.
It's amazing how
So
well,
as you can see here, the Global
years,
Hawk has no yoke or stick to fly with. We use a mouse for So as you can see here, the Global Hawk has no yoke. Underway. Everything is automated in the Global Hawk. So all I need to do is do a mouse click here on the screen to say takeoff or to land, climb, descent, maintain an altitude. Everything is done by this mouse click. And it's very much like flying an autopilot in a manned airplane. Yoke or stick to fly with. We use using this as takeoff to as landing, a study climb and descent when underway. Everything is automated in high impact weather events. So all I need to do is do a mouse click here on the screen to say takeoff or to land, climb, descent, maintain an altitude. Air Force C-130s. Everything. We're going to be working with NOAA Gulfstreams and also a NOAA ship, the Ronald H. Brown. So we've got C-130s covering one part, G4 covering another part, the ship covering other stuff, and then we're going to be in the parts that are harder to reach.
We typically take off at first light so we can get to the area of interest to study El Niño weather per the science requests. This usually takes about maybe 8 hours to transit to the area that we're studying. And once we're there, we spend several hours analyzing all kinds of weather phenomena that has piqued the interest of the scientists. And it usually takes about 8 hours to bring the plane back home. So that gives us about a total flight time of 24 hours for each sortie. I'm Herman Posada, and I'm a UAS research pilot here at NASA Armstrong Flight Research Center, and I fly the Global Hawk for airborne science. While we're flying the aircraft, we're monitoring many screens. Mostly we're looking that we're on the right track that science has requested us to fly on. We are also obviously looking at various parameters of the aircraft, make sure we don't get any trouble with airspeed, altitude, or the heading. The flight plans continuously getting updated as science changes the area of interest. Obviously these storms are moving and we are trying to keep up with them.
Hey, mission payload.
So in the Global Hawk Operations Center during a flight, we're going to be monitoring the flight with this wonderful mission tool suite capability that NASA has developed. And with that, it allows us to see the data coming in from the aircraft in real time, satellite data, and multiple things for us to really see what's happening as we go along. And so what we'll be watching for is, can we see the weather patterns? Can we see patterns in the humidity that let us know that we're sampling the areas that are eventually going to move downstream and impact the U.S.? The Global Hawk is a one-of-a-kind capability that, NOAA, we have a great observing system from satellites to aircraft to ships, but there's nothing that provides the capability of the Global Hawk. So within NOAA, we really want to see if that is a really good addition to our current observing system. And so by collaborating with NASA, we get this wonderful opportunity to test its capabilities, see its impact on the forecasts, and then hopefully that opens the door for a broader collaboration down the line to do this on a regular basis.
Copy, and these will be in any right turn away from you.
This is a lab, measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA but from many universities and other government labs and organizations. And together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The Chorus AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the Chorus AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or lidars, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure air quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to connect what the satellite sees with what's at ground level.
Chorus AQ has in its team 2 smaller aircraft equipped with atmospheric chemistry measuring instrumentation. A King Air from NASA Langley Research Center, and a King Air provided to the Korean National Institute for Environmental Research by Hanseo University.
The Hanseo King Air aircraft is relatively smaller than DC-8 in NASA. It can freely access source of pollution and measure air quality capital territory that cannot approach using DC-8.
Working all together, scientists from the Chorus AQ campaign will provide valuable data and test the technologies needed to better understand air quality and the flow of pollutants within our atmosphere.
We can only fly the planes for a very short period, but the details that you get from the aircraft help inform the observations from space and from the ground, and how models can interpret those observations.
From this mission, we'll have better models and better mission data for Asia, and so we'll be able to extend the usefulness of this well beyond South Korea to other developing cities around the world.
We have the tools to study our atmosphere. Now, let's go exploring. Get to work at 5 o'clock. Morning briefing at 6:30. It's just another day at the office. Or is it really?
There's a lot to juggle in the field, so life in the field can be quite hectic. It takes 3 hours to do a full warm-up of all the instruments on this aircraft. That means a start at 5 a.m. in the morning and a takeoff at about 8 a.m. The forecasters will look at the conditions to verify that the flight is ready to go, and the plane will take off for an 8-hour flight.
So, if you're a scientist studying air pollution, where should you be doing your research? Yep, that's right, in the air.
And once the plane takes off, the fun begins. There's a lot of talk on the headsets about what we're seeing and whether it makes sense in terms of what the models had predicted. Don't forget that this aircraft is flying in the atmosphere to verify whether the models can do a good job of predicting air quality. Each flight begins with a pass through the city of Seoul for a chance to see what that looks like. And then we'll go to high altitude to fly along the peninsula along a route that we've chosen and looking down with what we call the LiDAR. The lasers that point underneath the aircraft provide information on the pollution levels at different altitudes down toward the ground. And we have to use that information to decide where we will want to sample in altitude along that same path following the LiDAR paths. That 8-hour flight does not stop us from continuing forecasting on the ground and trying to give information to the flight as it happens in case conditions change. And so those days can be very busy between planning tomorrow's flight but making sure that today's flight happens well.
There's a lot to do on the flight days for the scientists on board the aircraft. However, there are other teams that also have to be working around the clock in order to have these airborne laboratories ready for investigating the atmosphere.
On this mission, the maintenance crew is pretty busy. We've got so many scientists on board. All the scientists have different needs and requirements, such as changing out some of the gases they have on the airplane. They also need to definitely make sure the airplane is pre-flight right, so we're good to go. Check out a lot of the systems. They're refueling the airplane. Before the flight, they take off all those covers off all the probes, which actually takes quite a bit of time. And then after the flight, they need to put those back in place. So I mean, the maintenance crews are the guys. They're the first guys to show up in the morning and the last guys to leave at the end of the day. They make sure we have a good jet for that day's mission. And if we break the jet on that mission, they're the ones who've got to fix it and get it ready for the next one.
Teamwork is the key to a successful campaign. The Chorus AQ mission involves the coordinated effort of over 500 people.
So we have about 505 people registered on the mission website, and of those, about 300 have been active participants at some point during the deployment, and we had to ensure that everybody had access when they needed.
Scientists, crew, technicians, but also equipment, supplies, logistics. A massive scientific research mission requires planning ahead and effective management.
Preparations for something of this size begin years in advance. And so, having already visited here with the Earth Science Project Office several times, we were able to put together a situation that would enable this many scientists and this many resources to be put into play.
ESPO was involved in all phases of the mission, from its conception to its planning and the implementation. We need to understand what the researchers want, which become our requirements, and then we come here and see how we can best meet those requirements, whether they are logistical or operational.
The Earth Science Project Office is in charge of managing the mission. Anything you need to accomplish your objectives during the mission, they are the people to go to.
Entering a foreign country is very difficult with all of the things that we bring. Operating in a foreign country is difficult because their airspace is very busy and maybe some of their procedures are different than ours. And keeping the flow of people and information and equipment smooth and in a way that does not interrupt or distract us from the science is a great talent, and we appreciate the Earth Science Project Office's support.
They are the ones making sure scientists have everything they need to keep working every day. So if you want to do a good job, you have to go to the right place and measure at the right time with the right people. And for these people, the right place is in the air. Although in the end, for them, maybe it wasn't just like another day at the office.
Yeah, it's a totally different experience.
The work we do here day to day is much different than what we do in the lab.
I've been waking up pretty early at about 4 a.m. and then we get out here at about 5 to warm up our instrument because the laser takes a while to warm up to peak power.
We'll be taking out gas cylinders and putting in new ones.
After every flight, we switch out the air canisters for the next day's flight.
Filling water or calibrating the instruments, making sure they're running correctly.
And then we come back out and mess with the laser a little more.
So I've definitely developed my muscle mass here.
You know, it's a lot of work, but it's also a lot of fun, and definitely different from just working in a lab or in an office all the time.
6, 4, 3, 2, 1, and liftoff.
For the first time in my life, I saw the horizon as a curved line. It was accentuated by a thin seam of dark blue light, the atmosphere. This was not the ocean of air I had been told it was. I was terrified by its fragile appearance. In 1983, German astronaut Ulf Merbold, on board NASA's space shuttle, was struck by how vulnerable the layer that protects us from outer space really was. He was right. Industrialization and economic growth have given us many commodities and technologies, but they have also generated a dangerous side effect: pollution.
Air pollution has a great impact on human health.
More than 7 million people die per year due to the effects of air quality.
It's a big problem. Populations are growing, and the impacts on health are an economic cost that I think governments are very interested in.
Understanding how we are affecting our atmosphere and the quality of the air we breathe is essential not just to continue developing our societies, but also to our health and therefore our survival. By combining measurements from satellites, ground stations, and aircraft over the South Korean peninsula, CORUS AQ will create the most complete picture of air quality ever measured.
As atmospheric chemists, we do know a lot about the basics of air quality, but the specifics of what happens in Korea are not something that we know a lot about.
It's not a mystery to us that there's a lot of air pollution. What we're really trying to do is learn how we can best help the South Koreans improve their air quality.
Government is trying to come up with a better strategy to fix this issue, but it's not that easy. You know, it's very complicated scientific issues we are facing. So I think this mission really helped us to understand what is going on in our country.
But air pollution is also an environmental problem common to other cities in many countries.
It turns out that there's many cities around the world that have similar problems to Seoul, even in the United States. And so this field study will help improve the models and the processes in the models that will benefit many other cities around the world.
The information gathered throughout the CORUS AQ campaign will help us improve our models of air quality and better understand the flow and interaction of pollutants in our atmosphere.
Almost anyone who you tell about the CORUS AQ experiment will immediately ask about how much of it's coming from China. Transboundary pollution is always a concern, and we came here to look at that as well. But we've had the good fortune of having a weather condition that has created a lot of stagnation in the Korean country and has prevented Chinese emissions from having a large impact on Korea.
Yeah, we sort of expected that frequently there would be pollution from China blowing over Korea. But due to the meteorological conditions this year, that didn't seem to happen very much.
It turns out on some days the emissions from China is impacting South Korea, but on many days that we're here, it's entirely due to the pollution emitted by the 51 million people living in South Korea.
And what we believe is that this will motivate the Koreans to understand that they can make a difference in their own air quality by making local changes of things that they can control rather than worrying only about what's coming from outside.
Having detailed information on the sources causing air pollution is one of the most important outcomes of an air quality study. Decisions can be made in order to address environmental issues on a region.
We have also seen that the position of some emission sources, in particular with Seoul being in the northwest corner of the country, and also many of the power plants and chemical facilities upwind of the city, that the location of some sources is potentially creating a bigger problem in Seoul than is necessary. So looking at the balance of where activities are located in Korea is likely going to be a topic of interest for the outcomes from CORUS.
Real-time measurements of emissions over the Korean Peninsula has already proven the importance of this field study. Further and more detailed analysis of the data collected during the campaign will help scientists improve air quality models.
So now we will have the 6 weeks of data of hundreds of different compounds to evaluate our models with, to see how they do during these 6 weeks. And then if we can make our models reproduce this period, reproduce all the observations we've made, then we can have confidence that it will work well next year or next fall.
These models also help us test how we can best reduce the air pollution by what if we cleaned up the cars? How much would that help? What if we cleaned up the power plants? How much would that lower air pollution? So these models are useful tools to look at different scenarios.
It's relatively simple to filter out or scrub emissions, but it's not inexpensive. So if you know which ones will have the largest impact, then you can target those and still have good economic productivity and protect your population.
Computer models can help assess air pollution problems and guide politicians in the decision-making process to lessen industrial impacts on the environment.
We definitely have technologies that will help us with air quality, but the economic factors always come into play. And so people are always looking for ways to do things more economically, but that doesn't always mean doing them cleanly. And so regulations are needed to make sure that we don't take shortcuts and that we make the proper investments in making sure that our activities are not having an undue impact on the environment.
After weeks of hard work and intense data collection, the CORUS AQ field study has enhanced our knowledge of our planet, our understanding of the complex processes that take place in our atmosphere.
With CORUS AQ, we take another step toward the future of an air quality observing system that is going to make us able to be more effective in identifying where poor air quality is developing and how to better understand what's driving it.
What we've learned here can also be applied to other cities and hopefully can help us improve the air quality around the world.
Because I think the air pollution issues is not only for us, but also from some other countries.
We are paving the way to better understand pollution and our impact on air quality in our atmosphere. But there's still much work to do ahead of us.
Well, I think that as we reach 7 billion people on this planet, the consequences of what we do have a very significant impact on the environment, and we need to understand what we're doing very well.
So this is the first step of a long journey. We will still need additional aircraft measurements and ground-based measurements going forward.
We can't be everywhere with the plane. But now that we demonstrate here how the plane works in concert with satellite observations on the ground, we can use satellite observations to point the aircraft to the places where we can learn the most, or the places that are in most need of understanding what's going wrong.
So we must continue investigating, exploring this world to improve the lives of all of us who call this planet home.
When you put a human being in a spacesuit, suddenly the impossible is possible. Since 1965, NASA has conducted hundreds of EVAs, short for extravehicular activity.
So when I think of EVA, I think of the symbolism of a fellow human being existing for even just a short period of time, alone and separated from nearly everything else, And I think of that symbol of that single person representing our species and representing our voyage of exploration.
Before exploration can take place, before a human being can step outside the spacecraft, another mission must be accomplished: the creation of the spacesuit. Throughout the history of EVA, NASA has sought to build the best spacesuit and tools to match the job required for the mission. For our suit engineers, this means designing, testing, and redesigning to get it right. During Gemini, our designers were faced with a tough challenge to create the very first U.S. spacesuits. Suits that would allow astronauts to work outside the spacecraft in low Earth orbit. Building on that experience, new suits were developed for the Apollo missions. This time, astronauts needed to walk on the moon while carrying their own life support on their backs. With planetary surface exploration as the objective, the suit had to bend and move to facilitate tool use and protect the human. During the shuttle years, NASA redefined what could be done with EVA suits and tools, retrieving broken satellites, rescuing and rebuilding the Hubble Space Telescope, and building the International Space Station. The same shuttle spacesuit is on the space station today. It allows us to maintain and repair our home in space. But what about future missions? What kind of a suit will we need? Will we be walking on a planetary surface? Floating in microgravity? Or both? NASA is already investigating the next generation of spacesuits, creating a variety of prototypes to prepare astronauts for the journeys ahead. The Z2 is one of those prototypes. Its sleek design looks different from any other spacesuit NASA previously built.
We were able to take some artistic license on this prototype spacesuit and have some fun with it and engage folks out around the country for what they would like to see in a spacesuit. We worked with Philadelphia University to do the initial layouts of the suit, and then we have some in-house fashion designers that also help build our spacesuits, and they were able to bring their experiences to it and evolve that cover layer to make it even better than what we started with.
The Z2 isn't just fashion forward on the outside. It's also technologically advanced on the inside. This is one suit made for walking, on other planets, that is.
To be a planetary spacesuit, some of the special features on the Z2 are boots specifically designed for walking and for keeping your foot integrated into the boot well, like a good hiking boot. It also has a lot of lower torso mobility that allows you to walk naturally so that you can go uphill, downhill, into craters, pick up a rock, as a geologist would want to do on a planetary surface.
Like any prototype, NASA hopes to learn a lot from the Z2 as it continues to improve and develop spacesuits.
Prototypes are really important for spacesuit development because you can only do so much in the modeling and analysis world. You really don't know how well the suit works until you integrate it with a person. You get the feedback that a person can give you. You have them walk around, you have them try different tasks. That's how we really know that we've done a good job designing a spacesuit.
Another suit in the works is the Prototype Exploration Suit, or PXS. This suit could be used for EVAs in microgravity, or it could be further modified for walking on planets. As with all future spacesuits, NASA is wanting to see better mobility, more visibility, and better control and communication.
So one of my main responsibilities on this spacesuit is the suit control assembly, and that's the box that sits right here on the front of the suit. And it allows the crew member to control their life support components, such as their cooling and their pressure, and it also controls a lot of the electronics, such as the radio and the volume, and they can see some of the data that's coming back and forth from the suit computer to that display. So one of the great things about this job is that after designing the box, I'm able to get into the suit, since it's one of the smaller sizes, and we can actually see what the limitations are with my own hands and eyes, and not just hear that secondhand from another test subject that would be looking at the same data. And then to take that back and then to go build the next prototype and incorporate the changes that need to be made so that it works better the next time.
Whether it's the PXS, or the Z2. New NASA spacesuits have a big job to do.
And that's not just being in a vacuum, but it's very hot, it can be very cold. And then in addition to that, there are little micrometeoroids that are flying past that you have to protect in case that does hit the suit. So there's a lot of things that go into protecting the crew member in addition to just being in a vacuum. And when we go farther to the moon or Mars, you have to protect in case you trip and fall. So there's a lot of protection that the suit has to take into account.
No matter where we go or what we do, spacesuits and EVA tasks will continue to change and evolve. To keep up, spacesuit engineers will use new technologies, new materials, and new ideas to help us on our way.
In the future, I'm looking forward to spacesuits that are much more of a tool for the astronaut, that is more integrated with the human, and is less of an encumbrance and more of a help.
I think of EVA as basically a ship of exploration, a ship of learning and understanding, both about what makes us individually human and about what makes us together a team that seeks to learn and understand what the truth around us is. And that search for knowledge, that search for truth is, I think, one of the most noble and meaningful endeavors that we can pursue together.
This is a story about heat. Heat in our atmosphere, our oceans, and land. When you think about it, events like droughts, hurricanes, and fires, all of those are just different ways we see heat expressed throughout the Earth system. You've probably been bombarded with a lot of intense headlines in 2020. Hottest temperature recorded here, largest wildfires there. It's been a lot to take in. My name is Leslie Ott, and I'm a research meteorologist at NASA's Goddard Space Flight Center. So the reality is the stage was set many years ago for these events. Over the last century, human activities have increased the concentration of greenhouse gases in our atmosphere. These gases act like a blanket, trapping heat and leading to overall warming of the planet. Many of these gases remain in the atmosphere for a long time, meaning that we'll be feeling the consequences of this trapped heat for many years to come. Which unfortunately means next year is probably going to bring a lot of the same kinds of stories that we saw in 2020. But taking a look at all the different ways our planet responds to the variations in movement of heat can help us better prepare for the future. Maybe one of the most obvious ways that we saw heat this year was through fire. I know the Australian bushfires were big news last January, and when you think about it, years of prolonged hot temperatures and drought really set the stage for these fires to be more likely and more severe. With drought and heat waves, we typically see an increase in the availability of dry fuels, which leads to more powerful fires. So when you have multiple years of intense heat, it's not surprising to have significant fire events like we saw in Australia. These fires were so extreme that we saw smoke injected as high as 18 miles above the surface. That's really important because when smoke is injected that high, it can have the same type of effect as a volcano, having these very, very broad impacts across whole hemispheres of the planet. At NASA, we use computer models like the Goddard Earth Observing System to help us study how aerosols and particulate matter move through the atmosphere. So we take these models, we input real-world observations and data to track fire emissions to help understand how they're forming, where they're going, and how much of an impact they'll have on you and me. In California, California, heat waves have increased fire risk, and as a result, we saw a lot of synchronized fire activity. That is, many dangerous wildfires burning at the same time. And unfortunately, these types of huge fire events are becoming more and more common across the western United States. And that's a big problem. This year, Siberia also had a remarkable and active fire season. What we saw was that temperatures in the region were much higher than normal for this time of year. In fact, the temperatures above the Arctic Circle broke records in many of the same regions where the fires were burning actively. In the Arctic and boreal forest ecosystems, heat waves can exacerbate fires. And in the Arctic, you also have to factor in permafrost, which is soil that's frozen for long periods of time, and that can make the impact of fires in high latitudes even more complex. When severe fires burn in areas with permafrost, we lose this important insulating organic soil layer, which accelerates thawing, and it's potentially releasing carbon that's been stored in the soil for hundreds and in some cases even thousands of years. And you sometimes see these zombie fires, which happen when wildfires burn deep into peatlands or smolder in forests under snowfall. If that temperature doesn't get cold enough to extinguish the fire, they can continue to burn over the winter, even long after the visible fire's been extinguished at the surface. So come spring, they reemerge and they continue to burn back on the surface again. Studying what happens in the Arctic is really important because it's warming about 3 times faster than the rest of the planet. And all those aerosols and the carbon that come out of the Arctic don't necessarily stay there. They affect the heating and air pollution in much larger regions of the planet. Another part of the planet affected by heat, of course, is ice. Land ice in the form of ice sheets and glaciers where we've seen significant melt in recent decades, and frozen ocean water, or sea ice. This year, the Arctic sea ice minimum almost reached a new record low. It was second only to 2012's extent, which was an anomalously low year in part due to unusual weather conditions. Sea ice shrinks and grows with the seasons. After reaching an annual minimum extent in September, Arctic sea ice begins to grow again as sea temperatures cool off for the winter. This year, Arctic sea ice had an unusually slow start to the regrowth period. In particular, the Laptev Sea, which is sometimes called a sea ice nursery because much of the Arctic sea ice initially forms there, was too warm for meaningful sea ice growth until much later in the season than usual. Oceans absorb heat from the sun, and our atmosphere prevents this heat from escaping back to space. The movement of this heat is one of the primary drivers of circulation and global weather patterns. We can measure the temperature of the ocean, and what we saw this year was unusually high surface temperatures across the Atlantic. The warm moisture that comes off the ocean acts as fuel to storms. So as this layer of the ocean gets even warmer, we're seeing that storms are becoming more and more intense over time. In fact, 2020 sea surface temperature contributed to an exceptional year in terms of Atlantic hurricanes. We saw 30 named storms, a new record, and 12 of these storms made landfall in the US. What's really interesting is that many of these storms intensified really rapidly. Not only are storms intensifying more quickly, but what we're seeing is that they're stalling near coastal regions more often, which is devastating in terms of floods and storm surge. While we're not 100% sure what is causing these storms to stall, it may have to do with climate patterns shifting in response to rising global temperatures. It's always really tough for a scientist to say any particular fire or any particular event was because of climate change. But we're getting to a point where we're starting to see season after season of record-breaking wildfire, season after season of really intense storms, that it becomes much easier to understand that this is likely the result of long-term climate change. In general, more heat means more energy in the Earth system. So while 2020 was a significant year, it's important to know that this probably wasn't an anomaly of a year. We're likely to experience many similar years as the Earth's climate gets warmer. So while we saw a small dip in emissions this year due to COVID shutdowns, it was pretty short-lived. The vast majority of our greenhouse gas emissions come from things like electricity generation, which were less affected by the shutdowns than emissions from cars and airplanes. But we know that human activities have a powerful impact on our environment. Long-term strategies to curb human-induced climate change would have to focus on implementing cleaner technologies so we can reduce emissions without affecting people's daily lives. So while this is a story about heat, this is also a story about connections. Nothing in our planet happens in a vacuum, and our actions today impact our tomorrow. The choices we make now can make the difference between continued increases in greenhouse gas emissions and 2020 being the year that they peaked.
The next commercial crew mission to the space station, an historic milestone on Mars, and a hearing to confirm NASA's next administrator. A few of the stories to tell you about this week at NASA. On April 23rd, NASA's SpaceX Crew 2 mission to the International Space Station launched from our Kennedy Space Center in Florida.
Mission and liftoff.
The mission is the second crew rotation flight of SpaceX's Crew Dragon spacecraft and the first with 2 international partners. The next day, the Crew 2 astronauts, our Shane Kimbrough and Megan MacArthur, as well as Japan Aerospace Exploration Agency astronaut Akihiko Hoshide and Thomas Pesquet of the European Space Agency, safely docked to the space station. They are scheduled to spend 6 months conducting science and research aboard the orbital outpost. On April 19th, our Ingenuity Mars helicopter made history on the Red Planet.
Altimeter data confirms that Ingenuity has performed its first flight of a powered aircraft on another planet.
The first powered, controlled flight on another planet by an aircraft happened in an area on Mars now known as Wright Brothers Field, so named to recognize the historic connection of Ingenuity's flight to the Wright brothers' first flight on Earth. Ingenuity rose to an altitude of 10 feet, maintained a stable hover for 30 seconds, and descended back down to the Martian surface for a safe touchdown.
We have done it. This is the first time I've been able to say we've done it. So beyond this first flight, over the next coming days, we have up to 4 flights planned and increasingly difficult flights, challenging flights, and we are going to continually push all the way to the limit of this rotorcraft.
Ingenuity successfully completed its second Mars flight on April 22nd, during which it climbed to 16 feet, moved sideways about 7 feet, made a few additional maneuvers, then headed back to the center of the airfield to land. Meanwhile, a first for our Perseverance Mars rover on April 20th. A toaster-sized experimental instrument aboard the rover, called the Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was used to convert some of the Red Planet's thin carbon dioxide-rich atmosphere into oxygen. The MOXIE technology could lead to systems capable of isolating and storing oxygen on Mars to power rocket launches from the Red Planet and possibly provide breathable air for astronauts on future surface missions to Mars. On April 21st, former U.S. Senator Bill Nelson, the president's nominee to be the next NASA administrator, appeared before the Senate Committee on Commerce, Science, and Transportation during a confirmation hearing on Capitol Hill.
If you ask me what is my vision for the future of NASA, it is to continue for us to explore the heavens with humans and with machines. And there is a lot of excitement.
If confirmed, Nelson would become NASA's 14th administrator. Nelson flew aboard the Space Shuttle Columbia as a payload specialist on the STS-61C mission in 1986. On April 22nd, Earth Day was all about connections to our home planet and to each other. Powered by the hashtag #ConnectedByEarth, our Earth Day virtual event April 21st through 24th celebrated Earth and the planet's more than 7 billion people of diverse backgrounds and experiences who all share a connection. The free online event included live panel discussions and chats with NASA Earth science experts, downloadable content such as coloring pages, activity sheets, ebooks, posters, and more. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
It makes one orbit in about 95 minutes, and so we do about 15 orbits a day. It's about 340 miles up in space, so Hubble is moving quite quickly. It's going about 17,000 miles an hour, which is incredibly fast. And so we have a 95-minute orbit. It'll vary a little bit with the orbital geometries.
Juliet Oscar November calling. Juliet Oscar November calling. NO1SS, it is 6 Juliet Oscar November. You copy me, Chris? Copy you loud and clear. Okay, I'm going to patch them through. Please, 1 minute.
This is Owen. How has seeing Earth from its orbit affected you, in your frame of reference when moving around the ISS, or in your perspective of humanity as a whole? Over.
Hi, Owen. That's a great question. Seeing Earth from up here it's a beautiful thing. It's just this peaceful place with no borders there, and you just see this wonderful colors of blues and greens and browns and white clouds and snow-capped mountains. And it really gives you an appreciation for Earth as a spaceship for 7 billion people, just like our spaceship is keeping us alive, and how we need to take care of Earth because it takes care of us. Over.
This is Spencer. What happens if you vomit in the space station? How do you clean it up? Over.
Well, hi, Spencer. Fortunately, we are prepared for vomiting in space, and we bring special bags that if we're feeling the urge to go, we use these bags. Occasionally, on the launch, it can surprise you, and but we have bags in the launch vehicle as well. If you didn't make it in the bag, it would be a real mess, and it would go everywhere. It would take quite a bit of time to clean up. Over.
This is Lucas. How has the COVID-19 pandemic affected you while you're in space? Over.
Hi, Lucas. The pandemic has affected us because it's affecting our families. Our daily life here on the space station is largely the same with or without the pandemic. We are safe and we are executing our job and keeping the space station running and functioning and keeping ourselves healthy with our daily routine. But we're concerned for our friends and family and loved ones because they're in Russia and in the United States having to deal with it just like you are. Over.
This is Allie. What will be your first meal when you get back to Earth? Over.
Hi, Allie. I like to eat, and so I'm looking forward to any food that somebody makes. But one thing we don't have is an oven here, so something that comes out of the oven and you smell those smells and you eat a nice hot meal, that sounds terrific to me. Over.
This is Sawyer. What does it feel like when the rocket lifts off? Over.
Sawyer, when the rocket lifts off, it's this tremendous feeling like somebody's pushing you in your back and shoving you faster and faster and higher into the sky. And there's a few periods of time where our engines change, it's called staging, and there's some bumpiness and a little bit of shaking in the spacecraft during those periods. But the rest of the 9 minutes is just like a giant force is throwing you into the sky. Over.
This is Jordan. What does the space station smell like? Over.
Jordan, the space station has not too different smells than you'd have in a home down there. We try to keep ourselves clean. We try to keep the space station clean. In fact, tomorrow is Saturday, and that's our cleaning day, and we do our best to keep it neat and tidy. But occasionally there's smells where we have to change fluid. A lot of times that has to do with our bodily functions in the toilet, and they can be smelly there. But for the most part, the space station, to me, it smells just like a normal home. Over.
This is Eric. Was training to be an astronaut harder or easier than training to be a Navy SEAL? Over.
Well, Eric, they were totally different. The training to be a Navy SEAL initially was very hard for 6 months. Training to be an astronaut or a cosmonaut is a long process, and it takes many years of hard work. So, and it's more academic, more having to do with your brain. In SEAL training, we had some academics, but largely it was a physical thing. So 2 entirely different programs. Over.
This is Owen. What experiment that you've done had the most unexpected results? What was the expected and actual outcome of said experiment? Over.
Wow, Owen, that's a very detailed question. We have lots of experiments going on up here, but one that when I first arrived, we were growing some plants, and I thought that they would grow more than they did. Over the course of several weeks, they were just a small sprout, which surprised me because pictures I had never seen growth in space before on my previous missions. So I'm looking forward to trying that again and getting better results. Over.
This is Spencer. How successful is your 3D printer on the station? Over.
Spencer, we have the 3D printer has been here since I think 2015, a few years, and we've printed many parts. We don't have it deployed and active all the time, but when we need to, we can print what we need if it meets the criteria. It's a very effective way of having spare parts in space. Over.
This is Lucas. We're a model rocket building club. Did you ever build model rockets when you were young? Over.
Lucas, I wish I did, but I never had a club or a mentor in my area that was involved with model rockets, so I never really launched a model rocket as a young person, but I think it's great that you guys do. Over.
This is Allie. What does microgravity feel like on your body? Over.
Allie, microgravity is more a feel of how to move around. Your body, in my opinion, feels kind of the same. Everything you do on Earth with your body, eating, going to the bathroom, sleeping, your hair growing, all that stuff is very normal, I think. But moving around in microgravity is not normal, and it takes some practice to get used to how to do it effectively. Over.
This is Eric. Does the Earth look any clearer or less polluted now compared to when you flew in 2009 and with Canadian Chris Hadfield in 2013? Over.
I actually flew with another Canadian, your Governor General, Julie Payette, in 2009. So this is my first mission in space without a Canadian crewmate. But the Earth does not look any different with our eyes than the previous times. And my crewmate and friend Anatoly has been in space several times, and we both have tried to see any differences, and we can't really tell with our eyes. Over.
This is Sawyer. Do you play any games while you are on the ISS? Over.
Well, Sawyer, we're pretty busy people up here. We have lots of work to do during the day, and by the time nighttime comes around, we just have the energy to eat and clean up from our day and prepare for the next day, maybe make a phone call or something, or answer an email, but we don't have a lot of time to play any games. Probably the closest thing to a game is seeing how straight you can fly without crashing into a wall and how far you can go like this. Over.
Well, I tell you what, for all the folks on the phone, let's go ahead and give Commander Chris Cassidy and the crew on NA-1SS a big round of applause anyway. Sending my greetings along to all of you in traditional amateur radio terms. 7 threes. Best wishes, and thank you for participating in this activity. Thank you, everybody. This is just excellent.
So we are standing in the Quest airlock, which is divided into two parts. We have the equipment lock and we have the crew lock. This equipment lock has a hatch right here that closes, and the crew lock has another hatch. The EMU, or the Extravehicular Mobility Unit, is our spacesuit, and it's divided roughly into two parts. We have the hard upper torso, which is almost like a turtle shell. It's a hard fiberglass shell, and then we also have the lower torso assembly. These spacesuits are our own little spacecraft, and they have everything you need to keep you alive out in space for 7 to 8 hours, maybe even longer, depending on how hard you're working. The only thing that they do not have, and they have radios, it has oxygen, it has carbon dioxide scrubbing, it has temperature control, it has everything you need except for one thing, a restroom. And so when we get ready for our EVA, the first thing we put on in the morning is a diaper, and that's our first layer. Then over the diaper we put on a pair of long johns, and that's to keep our arms and legs from getting scraped up. It also provides a little bit of wicking in case you're getting really hot and sweaty. The next layer is our liquid cooling garment, and the LCVG has little tubes running through it which allow water to circulate inside the LCVG to provide cooling when we're outside working really hard. So we've got the diaper, we got long johns, we got the LCVG, and then we're going to wear our spacesuit. 7 layers from the bladder on the inside, which maintains pressure, and that's a rubberized bladder, all the way out to the white layer on the outside. The crew member inside the spacesuit is also wearing this, what we call a Snoopy cap. It's a communications cap. We have a radio, so we can talk to not only to Houston, but we can talk to people on the space station and to each other. So we wear this communication cap inside the helmet. Also another key component of the EMU, or a spacesuit, is the helmet. You can see the helmet has a gold visor which protects us from the rays of the sun that we can bring down. It's pretty bright out there, and this gold visor helps reflect the rays of the sun so we can actually see and operate in daylight. At nighttime, we can raise this visor up, gives us a clearer view, and additionally we have helmet lights built into the helmet. On top of the helmet, we also have a television camera, so the ground is able to watch us while we work through these TV cameras. The work is really all done with hands, and so our gloves are really our most important piece of equipment in order for us to work outside. And one of the real challenges of a spacewalk is you have this heavy gloved hand, which is inflated, so it wants to stay like it's blown up like a balloon. But we walk by grabbing onto handrails and making our way along the ISS. So every time you move your hand, you're fighting against a balloon that wants to inflate. And then on top of that, all of our equipment is based on using your hands too. So after 6.5, 7 hours of kind of fighting against this glove, it's a really long day, and your hands are probably the thing that are most exhausted after 7 hours out on an EVA. Well, we're going out to work. You probably saw me move this mini workstation. The way we carry our tools is on a mini workstation, which is carried on the front. Every single tool we use is tethered to us. We do not want to accidentally create satellites. Our primary way of remaining attached to the ISS, if we're not using our hands, are these waist tethers. And you can see they just have a big hook. They go around a rail or anything else on the ISS and latch on, and it actually has a locking mechanism as well to hold us nice and tight. So we always want to have one of these attached if we're not holding on with our hands as well. The back of the EMU has our life support system. The life support system contains all the equipment we need, from a UHF radio down to the oxygen tanks that provide primary oxygen. One of the challenges inside this sealed environment, it's very easy to carry our own oxygen with us, but we generate a lot of carbon dioxide, particularly when we're out there working very hard. So to combat that, and to deal with that, we have these canisters called Medox canisters, which are just silver oxide, They are carried in the backpack along with a very large battery, which provides all the electricity for us. I don't have a battery here to show you today because we're in the process of charging them. We're about a month out from doing a spacewalk, and we've already started getting ready for that. So this Maddox canister is able to remove about 7 to 8 hours of carbon dioxide that a human can generate inside the spacesuit. EVAs have allowed us to build and maintain the ISS, repair mission-critical hardware, investigate malfunctions, install new hardware, and the view, unbelievable. See you next time.
Hi, my name is Jeff Bittner, and I'm a logistics specialist on the rocket train. This is rocket science in 60 seconds. Northrop Grumman is the manufacturer of the rocket boosters for NASA's Super Heavy Lift rocket, the Space Launch System. And we transport the boosters the same way we have for 3 decades, rail. The 21-car rocket train uses 2 engines, each producing 6,000 horsepower, to travel through Utah, Wyoming, Nebraska, Kansas, Missouri, Oklahoma, Alabama, Georgia, and Florida. That's a stretch of 2,800 miles over 3 railroads to deliver the motors to Kennedy. These rail cars are built to carry the immense weight of the 180-ton segments. It takes an entire day to load 1 segment on 1 rail car. Each segment is enclosed in a clamshell-like covering to protect it during travel.
When you think of sea level rise and NASA, if that's the kind of thing you think about, I feel like it's only natural to imagine scientists poring over satellite data, trying to better understand what's happening and what the future might look like on our coasts, including right here where I live in the Hampton Roads area of Virginia. My name is Joe Atkinson, and I'm a science communicator at NASA's Langley Research Center. This area is one of the hot spots for sea level rise in the country. Even on a beautiful, gorgeous, sunny day, we can have nuisance flooding just because of a high tide. But we'll get back to this area later, and specifically NASA Langley. The thing is, even as scientists are studying sea level rise, the agency itself is having to confront the reality of it. It has field centers and coastal communities around the country. I wanted to find out how seriously NASA is taking this threat. So I got in touch with a guy whose job it is to worry about this kind of stuff. His name is Calvin Williams, and he is the Associate Administrator for NASA's Office of Strategic Infrastructure.
First of all, I'd like to say thank you, Joseph, for the opportunity to speak to you about this. Sea level rise is a very major concern for us. We have about 2/3 of our NASA facilities are within 16 feet of sea level, and that comes to about $20 billion value of infrastructure that we have.
Now that long list of facilities includes Kennedy Space Center in Florida, Johnson Space Center in Texas, Stennis Space Center in Mississippi, Michoud Assembly Facility in Louisiana, Ames Research Center in California, and Wallops Flight Facility in NASA Langley right here in Virginia.
We have estimates that within the next 60 years or so, that there could be potential 4 feet rise in sea level. And so therefore we are trying to take measures now.
Now in broad terms, that means moving to higher ground or, making facilities more resilient. At 2 of NASA's launch sites, resiliency equals the movement of lots and lots of sand.
For example, we've done some reconstruction work at Wallops and also at KSC, where we have stabilized the shoreline and the dunes there. And that's something that we have to replenish approximately every 5 years.
So you have to wonder, is this something that would keep Calvin up at night?
Well, it is at the top of our list, definitely at the centers that are on the coastal areas. We want to make sure that we are taking the necessary steps to ensure that in the future we have launch facilities, research facilities that can continue the mission of NASA.
Now, Calvin talked about the beach replenishment efforts at Wallops and Kennedy Space Center. But I kind of wanted to dig a little deeper and find out what's happening at two of NASA's research centers, Ames on the West Coast, and of course, I wanted to know what's happening here at Langley on the East Coast. Since I work at Langley, I knew exactly who to go to, and that's Loretta Kellerman. She is the director of Langley's Center Operations Directorate.
Certainly, we are a coastal center. It's on the coast. We're surrounded by two rivers, the York River and the James River, and along with the Chesapeake Bay. So a lot of opportunity for flooding and for sea level rise to present itself as a problem for our center. And so this is a big issue for us, and certainly one we've been addressing for some time.
Now, conservative estimates show about a 15-inch rise in sea level at Langley by 2080. More extreme estimates push that number as high as 49 inches, or about 4 feet. The center uses a flood tool as sort of a, I guess, like a crystal ball.
This tool is a great tool developed by our geospatial information systems folks, our GIS team, that allows us to visually picture the rising sea level and which facilities and areas are affected.
In 2011, following a study that highlighted some of Langley's biggest vulnerabilities, the center, which is actually NASA's oldest, it's just over 100 years old now, began taking action in the form of a major revitalization effort. This effort aims to shrink and consolidate Langley's campus and minimize those vulnerabilities.
We've been demolishing facilities that are in high vulnerable areas and building all of our new facilities and consolidating a lot of our missions into fewer facilities at our higher elevations. And for us at NASA Langley, our higher elevation is around 12 foot. And so we're not very high here.
Further complicating the issue at Langley is a phenomenon known as subsidence. The ground the center sits on is slowly sinking by about 2.2 millimeters a year. Now, if you add that to the 4.6 millimeters of sea level rise a year, let me do the math here. You're actually getting about 6.8 millimeters of relative sea level rise a year at Langley currently. The center isn't taking any chances. They can't pack up and head for the mountains, of course, but in addition to squeezing the campus onto the highest possible ground, they're also making really smart construction choices.
The study that we did in 2011, of course, recommended that we build all of our first floor elevations to 10-foot, 6-inch minimums, and that goes into our design requirements for all of our new facilities.
For Loretta, sea level rise isn't just a work concern, it's a personal concern too. She and her family live right on the water. But the communities in Hampton Roads are taking the issue seriously, and the federal agencies are too. So she takes heart in that, not just as a federal employee, but also as a private citizen.
I'm on the water. I always say I'm on the water or I'm in the water, depending on the storm that day. So you just never know. So it is a little personal and a little drives a little anxiety, but I'm very encouraged by certainly the work that the city of Hampton's doing. And I think the things that they'll do will continue to support, and they're very engaged in the federal community here in Hampton. And I think all the things that they're doing are going to help our center as well to try to move water out and away, from the city.
Okay, so now we're going to move all the way across the country to Ames Research Center, which is in Mountain View, California, right in the heart of Silicon Valley at the southern end of the San Francisco Bay. Now, when I reached out to Ames, they put me in touch with a guy named Garrett Turner. He is the Restoration Program Manager in the Environmental Management Division at Ames. And when Garrett thinks of sea level rise at Ames, he thinks back to 1998 and a series of storms that moved through the area. Now, this gave officials at Ames a big scare because it flooded the north end of the center and threatened to inundate a telecommunication gateway facility there, which actually would have shut down the internet for all of Silicon Valley.
We managed to keep that from happening by getting a lot of employees both civil servants and contractors to go and put sandbags out. And then we were able to pump some of the water in the channels over a levee into Stevens Creek. After that, we kind of decided that we needed to have a proactive way of at least addressing big storms.
Now, much like Langley, Ames, which is the second oldest NASA Field Center, decided it needed to look to higher ground. That decision was based on 100-year sea level rise projections.
We are now requiring a much higher minimum elevation for a new facility that gets built. So we have these little popped up areas, and our master plan has envisioned taking facilities that are in that 100-year floodplain and relocating them and relocating the entire campus farther south, which is several feet higher and has a much lower expected impact from sea level rise.
But there is a wrinkle here. It's not just the bay that's a problem at Ames. There's an old system of salt ponds and levees nearby that date back to the 19th century, and they further complicate things, and it's not a problem that Ames can just deal with on its own.
Levee maintenance is outside of NASA's property, and we can't go and fix all of these and keep them from pouring water into NASA.
One thing they're doing is working with the local water district.
We're working on trying to, figure out how we can reinforce those levees and potentially raise them. That we have, a bicycling and walking trail, the Bay Trail that goes around.
They'll have to look to their neighbors on either side for help too.
If we protect the levees immediately in front of us and they do nothing with theirs, we end up with the water just going over their levee and then coming in. So this is going to have to be a partnership, kind of regional with other stakeholders, to make sure that we can come up with a strategy that works for all of us.
One of those strategies is actually to turn those old salt ponds into wetlands, which would help slow the effects of sea level rise. It would also be a return of sorts to what once was.
Civil engineers have it perfectly. In the early 1900s, we drained all the swamps. Now we're creating wetlands. It's kind of reversing what we did before. So it's all part of the same training.
We've had a little change of scenery here, obviously. I wanted to wrap things up on my front porch here in Hampton. We're just a few blocks in from the water, and we're on relatively high ground. Still, worst case, long-term sea level rise projections would have me sitting in the water here. And even minor to moderate projections are pretty bad news for some folks right here in this neighborhood. Just a few miles across the water in Norfolk, that way, the high tide nuisance flooding I mentioned back at the beginning of this video is already encroaching regularly on urban areas and frequently makes city streets a gamble for drivers in all but the tallest vehicles. And so just as these coastal cities are having to deal with these wet realities, so too is NASA. When I set out to do this, I really had very little idea what NASA was doing to deal with sea level rise itself. Now, after talking to Calvin and Loretta and Garrett, I realized that there's a lot going on. In some cases, there are things that centers can do similarly, like move facilities to higher ground to help. But there's really no one-size-fits-all approach. Every place has its unique consideration. Ames has the levees and salt ponds. Langley has subsidence. Kennedy and Wallops have beach erosion to deal with. Staying ahead of this stuff is obviously a big, big job that requires a lot of expertise, foresight, planning, and coordination. Thankfully, it's a job that NASA is taking seriously. And it's a job that will allow NASA to continue its critical work in space exploration and aeronautics and earth science, even as the water keeps rolling in.
Hey everybody, this is Beck, and I'm a maker of music. And like the great Sun Ra said, space is the place.
And I'm Farah. I work at NASA, and I use AI to explore Mars.
And I brought a few friends along who know something about artificial intelligence.
Hi, I'm John.
Hi, I'm Isabel. We are both artists working with NASA using artificial intelligence.
This is Ask NASA.
Yeah, so Beck, you just released a set of new music videos using a lot of NASA imagery, and I grew up loving space, and obviously those images are used by scientists. What inspires you about space, and how you came up with this idea?
Well, the title of the record came from a video game, a really primitive video game from the 80s called Asteroids. When the asteroids were going to kill you, and they were just about to collide with your spaceship, that you would hit this button and it would make you disappear and reappear somewhere else in the galaxy. And I always wondered what that button was called, and I looked it up one day, and it was called hyperspace. So I sort of, it got my mind thinking into music and song ideas. Because I think in some way, I think of music as sort of a hyperspace button. You know, it's something that we press play on a piece of music and it takes us somewhere out of our lives, out of our circumstances. But I did like the feeling of the music, that there was this sort of thread of outer space, kind of wide vista of space and time, existing in the songs.
Artificial intelligence is the ability for machines or computers to make autonomous and intelligent decisions. That can look like recognizing patterns or analyzing images or learning certain behaviors and then mimicking them.
I mean, right away when we heard hyperspace, we thought we have to use AI for this. Beck was already creating a sonic environment that went to like the edges of our understanding and the way that we see. And that's something that we're most excited about working with AI with, that it expands our modes of thinking. And then just the title, hyperspace, literally means to go beyond 3 dimensions. The one that we use for this particular project, it literally works in a 512 dimensional space. The process begins with the AI training on the images. So if we showed it just a few hundred, it wouldn't know that much. But what was so great about working with NASA's decades deep, archive of knowledge is that it could really learn. So for weeks and weeks, the AI trained on as many images as we could show it. I think in the end, it looked at over 25 million images. Sometimes that was multiple times looking at the same images to try and understand these images.
Yeah, basically imagery of anything in our solar system is how we get started in the process of exploration, right? And so when we first went to Mars or when we sent Cassini to Saturn, we had some thoughts about what we might find based on that imagery, and that's what allows us to really focus down on the type of science we're going to do.
I worked a lot on the database creation, and I feel almost like I could draw a picture of the galaxy now just from going, like anyone can do, just by working with the NASA websites and going through the archives. Like the AI was then able to take that and recognize colors that were happening a lot, recognize shapes that were happening a lot. I remember when it first showed us what it thought Saturn looked like, I was blown away.
Yeah, and even then, seeing these images and getting all the info, it is overwhelming, isn't it? I mean, we're talking about other worlds, we're talking about other realities we probably won't ever get to experience in our lifetimes. This is the closest we'll come to touching the unknown. This project is so interesting because it really came out of the theme of the record. I would have loved the idea of taking sounds from these missions in space and putting them into the music itself.
The coolest thing that we have coming up which we can point you to when it comes out, is that Perseverance actually has 2 microphones on board. It's the first time we'll have real audio from Mars. So we'll have audio as well landing on the planet, so that during entry, descent, and landing. And then we'll have audio when we're driving, or the rover has a laser, and so you'll be able to actually hear that laser zap on another planet, which is kind of something that's kind of hard to even wrap your mind around.
And that hasn't been recorded before?
No, not with a microphone, not this way. We've never had a microphone on the rover like that.
Okay, well, send those audio files my way when you get them.
Absolutely. So on Perseverance, we actually have an extra computer, and so that extra computer allows us to make the rover smarter. And we actually self-drive on Mars. So the rover has to take imagery of the area in front of it, literally build its own map. It can then identify different types of obstacles and slopes, and based on that and its knowledge of where it's able to drive, it decides on the path.
The Mars database was in one of the easiest ones because it's where we have the most high resolution imagery. It's been so well captured from so many different points of view.
We've seen the soil on a terrestrial level, and then we also have imaging of Mars from above, and looking through this data set of massive data set of incredible images. Once we trained the AI on that, it was able to kind of produce such vivid, strange imagery, because Mars itself, I think, is so much more complex and so much more deep and varied than we imagine it is.
Okay, so one more cool feature about the Perseverance rover is that it can also act as a scientist. The rover can look at the environment around it, look at all the rocks, and say, hey, this rock over there looks really cool. Let me image it, use my laser to zap it and figure out what's under that surface, send all of that data back to the scientists. So it allows us to essentially have scientists on Mars making decisions without having humans in the loop here on the ground.
I think, to me, the idea of space is a bit overwhelming and awe-inspiring. Just the idea of listening to a piece of music and we go somewhere else, our lives change. It's a mirror to this other idea of space and space exploration. And letting the imagery of these other worlds, these unknown places with this music, I think has been really satisfying to me. I feel really fortunate to have you all open your doors to me and my music, and for us to go somewhere with it that was unexpected, even for me.
Let's see, make a space or something.
Here, let me get my video up.
Sorry, guys.
We'll get it. We'll get there.
We'll get there.
NASA. This is Ask NASA. I mean, that would be the show tune way. There's all kinds of guitars. This guitar is actually from 1901, and it has these ivory pegs. All right, so these are some vintage keyboards. And this is the 808, which is responsible for the sound of all trap music. This is the Moog. And this is responsible for most of the music of the 80s. There's a couple of pedals that I use. Little bits and bobs.
By the time the Hubble Space Telescope was nearing its 10th anniversary in space, it had already become the gold standard for modern-day astronomy. Hubble had grown into an indispensable tool used by scientists all around the globe to take an inside look into the universe around us. Everything was great, flawless even, until something unexpected started to creep its way into the picture.
In the last month, namely in November 13th, the fourth of 6 gyros that are on board Hubble failed, and that left only 2 operational gyros.
Lights out. Hubble's gyros, which are needed to accurately point the telescope, were failing. What was NASA supposed to do? Cue servicing mission 3A.
And on Christmas, Discovery Houston, go inside the cockpit. Next scene.
So I propose no change, and then you tell us you go up there.
By 1999, Hubble was about to make its mark in the 21st century.
Discovery, go for Hubble release.
And as that turn of the century neared, Hubble was also due for another servicing mission.
I mean, you can just take it in, JT.
Just like the previous 2 missions to Hubble, Servicing Mission 3, planned for the year 2000, was going to upgrade and refurbish the telescope.
Hey, Store, what do you think about you putting your tether on?
However, without warning, Hubble's gyroscopes began to fail over a year before Servicing Mission astronauts were scheduled to launch.
The gyros, of course, are required for the science mission. They're required for the extremely accurate pointing. We've homed in onto a wire there that is broken, and we think that is the reason why the gyros have failed.
So, Hubble needed 3 gyroscopes to continue to do science, and by April 20th, 1999, that's all Hubble had. Swiftly, NASA declared a Hubble emergency and split the upcoming servicing mission into 2 parts. Servicing Mission 3A would mainly tackle the gyroscope failures, and Servicing Mission 3B would encompass the rest of the maintenance that Hubble didn't need right away. It was now crunch time. Not only did NASA have to prepare an extra shuttle mission, but the astronauts now had to go into overdrive to prepare for the upcoming mission, now scheduled for October. And then, when everything seemed to be more under control, news broke. The 4th gyro failed.
Today, it's sitting up there with its self in safe mode. And that, again, shows how important the serviceability is to this facility.
Hubble was now in safe mode, which meant that the telescope's eyes were temporarily closed to science. The servicing mission was more critical than ever before. And after multiple maintenance and wiring checks delayed the shuttle launch, on December 19th, 1999, the team of Servicing Mission 3A was finally able to make their mark on history.
And liftoff of the Space Shuttle Discovery on a mission to repair the Hubble Space Telescope as we venture into the 21st century.
Houston Discovery, roll program.
Roger, roll, Discovery.
Houston is now controlling, and roll maneuver is complete. Discovery is now in a heads down position, on course for a 28.5 degree, 310 nautical mile orbit.
Right away, the team of 7 astronauts went to work. This 8-day mission included 3 spacewalks to Hubble. The first of which replaced all of the gyroscopes. Now Hubble was able to be accurately positioned and stay locked on to its celestial targets. Not only that, the team behind Servicing Mission 3A refurbished Hubble's fine guidance sensor for even greater precision in pointing the telescope, fixed damaged thermal blankets that protect the electronics housed inside of Hubble, installed a new computer 20 times faster than Hubble's original computer, replaced old tape recorders with a new solid-state recorder for greater efficiency in Hubble's data management, and fixed the spacecraft's S-band transmitter to continue to relay data to the scientists on the ground. And on Christmas Day, 1999, Hubble was released back into the stars, ready to uncover new discoveries that lie ahead. Servicing Mission 3A proved that NASA could not only be quick on its feet in dire circumstances, but perform as a team that is united around keeping our eyes open to the universe for many years to come.
We've all played these claw games before where it can be really frustrating using a grapple to pull a toy out of a machine. Well, the success of NASA's InSight mission depends on a grapple. Let's learn about it on this episode of Crazy Engineering. All right, we are here at the InSight Lander Surface Testbed. This is Nick. He was one of the key engineers on the grapple mechanism. Nick, thanks for joining us.
Sure.
If we got this grapple, what does it do? What's its purpose?
So its purpose is to grab the instruments so the robotic arm can then lift them and place them down onto the surface.
When I play these arcade games, right, they're really hard to get that toy out of the game. And you're using a mechanism that kind of reminds me of that. Is that a good idea?
So the mechanisms themselves, although they look similar, are very different. With the arcade game, when you grab that stuffed animal and you pull on that stuffed animal, you actually open the claw fingers and that stuffed animal falls out. With the InSight grapple, that mechanism is designed to latch. So once those fingers are closed, it's impossible to pull on those fingers to open it.
So how does it work?
So the grapple has 5 fingers, and we designed this grapple to maximize our success. It uses a wax actuator to open the fingers. We grab onto little hooks at the top of each instrument, and then the robotic arm picks those instruments up and places them down on the surface.
You said wax, that we're using wax to open and close the grapple?
Yeah.
Why do we use wax? Why don't we use a more typical solenoid or an electric motor?
It's actually a thoroughly proven technology. It's used in space applications like the InSight grapple, but it's also used for decades in things like our car thermostats and our appliances at home. It uses a heater to melt some wax inside of a little housing, and when this wax melts, it expands and it develops this hydraulic pressure, and that pressure pushes out a rod which we use to actuate our mechanism.
Once it's completed its primary function of putting the instruments down, what does it do after that? How does it get out of the way for other things you want to do?
So there's actually another hook on the side of the robotic arm, and the robotic arm can maneuver itself so the grapple can re-stow itself on the side of the arm. Then the arm is free to essentially do whatever it needs to do.
Nick, this grapple mechanism is truly unique. It's really fun to learn about. Thank you so much for bringing us into the test bed and answering all these questions. And as always, thank you out there for paying attention, and check back here for some more crazy engineering.
NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello and a very pleasant good evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the Von Karman Lecture Series, our first of 2021. Tonight we'll be delving into the unique engineering of spacecraft origami. Now, origami as an art form dates back thousands of years, but in terms of engineering, it really only started to blow up in the past 20 to 25 years. Origami gives our technologists a useful and fruitful way of solving problems. Now, speaking of problems, if we run into any technical difficulties or small failures, we ask for your patience and stick with us tonight as we get them sorted out. As always, we like to remind you that this is your space program, and we want you to be involved in the conversation. Please ask questions in the chat, and we will try to implement as many as we possibly can throughout our discussion this evening. If you do not see the chat, go ahead and refresh your page, and it should be right there. And joining us as co-host, fielding your questions this evening, is our public outreach specialist, Talia Khan. Hi, Talia.
Hi, Brian. Thank you for that introduction. And thank you to all our viewers at home for joining us this evening. As a reminder, we will be taking questions through the chat and Facebook. So please feel free to pop your questions in there and we will get to them throughout the evening. Now I think it's time we get this show started. Brian, back to you.
All right, back to me. And yeah, let's get this started. We've got two speakers this evening. And our first one is a technologist in the Advanced Deployable Structures Group at NASA JPL. His research interests include large, unfoldable, origami-inspired structures, ultra-thin composite materials, and thin membrane structures. He received his PhD from the California Institute of Technology in 2016. Before we started, he reminded us how much he truly loves his job. Please welcome Manan Arya. How you doing, Manan?
I'm doing well. How you doing, Brian?
I'm doing great tonight because we get to talk about this wonderful little, it's not little at all, this wonderful technology. What was your inspiration? How did you get started with this in particular?
Well, so when I started in graduate school, I was really fascinated by these spacecraft called solar sails. And these are these spacecraft that unfold out these incredibly thin, incredibly large gossamer membranes, sails that catch sunlight, that generate thrust through the pressure of sunlight bouncing off these very lightweight sails. And I was really interested in thinking about how we may enable smaller and more lighter weight spacecraft to unfold out these large sails. And the problem ends up being, how do you unfold out these large, almost tennis court sized sails and fit them into tiny satellites? And that got me into thinking about, well, how have other people approached this challenge? And it turns out that there's been a lot of thought and a lot of exploration of how to take these large sheets of material and fold them down, thinking about the mechanics and the rules and the physics behind paper folding or origami.
Mm-hmm. So this field, as we talked about, has already blown up kind of in the past 20, 25 years. It's a bit of an esoteric job description because you're thinking, I mean, talk about how this has really grown up in the past couple decades.
Yeah, so origami, as you said, exists as an art form for thousands of years, and it's only in the past, century, half century, that mathematicians and physicists and engineers have started thinking about origami in a way of thinking about the rules that govern the folding of paper, in terms of thinking about how do we design new forms, how do we design new forms of origami, and also thinking about what are the physics, what are the mechanics behind paper folding, and how can we apply those mechanics to something other than paper. So people have come at this field of origami science or origami mathematics or origami engineering in a number of different ways. We've had sort of computational geometers think about origami as a way of creating new forms and new geometries. We've had my favorite example is actually has a JPL connection. His name is Robert Lang, and he's a giant in the field of origami engineering. But he used to be a laser physicist back in the day, and he came at it from the standpoint of being able to describe sort of the mathematics that governs origami forms. And he has designed new ways, new algorithms for designing origami structures. And this field has really started to explode in the past 20 to 25 years when we've realized that origami is amenable to mathematical description and to thinking about really the mechanics and the physics behind paper folding.
Very cool. We've got an image of you standing in. It's a cool image because you're standing. It's almost like your album cover. You're standing there in front of your work. What is this you're standing in front of? And then we'll look at the next thing that you've got there and some of the work that you've been up to.
Definitely. So that is a prototype antenna that we worked on, and I must say that it's not just me who works on these things. There's a whole team of people involved in building these structures, and that antenna in particular was designed alongside Richard Hodges, Jonathan Souter at JPL, and Sergio Pellegrino at Caltech. And it's an antenna that's about 6 feet by 6 feet, and yet it falls into a compact package the size of about, a toaster oven. And the idea is to take this large antenna and package it into these very small satellites that are now becoming very useful, called CubeSats. And these CubeSats are sort of briefcase toaster oven sized satellites that you can send up for not a lot of money, but that can do incredible science, especially if you unfold out these large structures from these CubeSats. like that
Well,
antenna that I'm showing. Yeah.
Yeah, let's see an example of that. We've got actually something folding in on itself here.
Yeah, so this illustrates how that antenna would fold up. This is a structure that was a prototype actually that we made for that antenna. And yeah, this is made out of ultra thin, ultra lightweight carbon fiber materials. And as you see, it goes from being about a meter across by a meter across to that very compact package right there.
Very cool. We'll go to our next image, and I want to ask you, as we're looking at something like this, why is this important?
So it comes down to the fact that when we launch things into space, we are always restricted by how much volume, how much space we have available in our rocket fairing. Rocket fairings are only so much, only so big. And if you want a structure in space to be bigger than what is allowed in the rocket fairing, then we need to somehow find a way to fold that structure up inside the rocket fairing, launch it, and then unfold it when it gets to space. And this is important when you're trying to have large structures in space that are doing things like collecting solar power, where obviously the larger structure you have, the more power you collect and the more capable your spacecraft can be. Or as in the previous example, something like an antenna aperture, where the larger the antenna aperture you have, the more gain you have, the better you can communicate back to Earth, or the more resolution you have for doing things like remote sensing. So it's trying to break what is typically called the tyranny of the fairing. You have only so much volume available. How do we make structures that are bigger than that volume available to spacecraft in space?
Well, let's actually show you trying to defeat the tyranny of the fairing with a video of this really opening and closing.
Yeah, so this was a prototype structure that we made. So that's myself and my intern Chris taking this carbon fiber structure and showing how you can package up these sorts of structures in a compact way, but also that the structure, when unfolded, kind of sustains itself. It has stiffness on its own, and it's able to maintain its own shape under Earth gravity loading, like right there.
Very cool.
And this was a prototype structure. Sorry,
yeah,
go ahead.
No,
please.
This
was a prototype structure we developed to investigate how we may package up large solar arrays and structures like that.
Oh, wonderful. As we go to our kind of the last video, last little bit of us talking to you, and we'll come back to you later, we want to talk about what's next. And there's a cool little video that we've got too that gives a little example of it, but really, from your opinion, what's next?
Yeah, I think people have really started exploring the edges of what's possible with sort of traditional single sheet of paper origami. There's still a lot more to be studied about that problem, but people are now approaching this from the perspective of how can we extend origami? How can we make new forms that are not possible with just a single sheet of material? So the structure that you saw me unfolding in the previous video has this kind of wavy character to it that is not possible with a single sheet of paper. In the video that's coming up, we're exploring the kinds of forms that are possible by assembling structures in a modular fashion using components that are individually based in origami. So if you could have that
number 5,
that next
yeah, there we go.
So this was a proof of concept foldable robot that this brilliant intern Alexandra Harasti from Caltech developed for us this past summer, and it's excuse the motorcycles.
We're live, yeah.
This was a study into how can we take these sorts of robotic bodies, package them up in a compact way, such that when we go and want to do exploration with these robots, we can pack many of these robots into a mothership, and then when they get to their destination, we can deploy many robots for multi-agent exploration of a surface using these stiff but still foldable robots that you can package many of in a compact volume.
Very cool. Is there anything that our audience can do at home with this?
Oh, definitely. That's the wonderful thing about origami, is that it is really accessible to almost everybody who has a flat surface and a sheet of paper. I think we have a link to some folding instructions for folding up these kinds of wrapping origami structures. So this is a fold pattern that was developed for an effort called that was trying to mature star shade technology, and you can go to the website and there's instructions and a pattern that you can print at home and then fold to see how we're packaging up these very large structures into compact volumes by means of wrapping in an origami fashion. I actually have a tiny version of that over here. This is not exactly the same fold pattern, but it's akin to the fold pattern that instruction set provides you.
So everybody at home could start this tonight. They could go on there, they could print it off, and they could start folding, and they would have what you're seeing on that screen right now.
Exactly.
Such wonderful, and I know people are asking lots of questions today. So Talia, what's going on with the chat today?
Yeah, so we have lots of amazing questions in the chat. One in particular stands out. So Jared on YouTube is asking, repeatedly folding paper can compromise the crease edges. How do you overcome this when you're repeatedly testing solar sail deployment?
That's an excellent question. So typically, we tend to use paper for initial prototypes and initial studies of the geometry and the forms of these structures. But when we switch to using these kinds of structures for space engineering applications, we switch materials to something that's a bit more robust than paper. So in the case of solar sails, we tend to use space-grade thin plastic sheets. The jargon is polymer membranes, and these polymers tend to be space grade and a lot more robust than paper. So in the case of solar sails, we think of polymers called polyimides, which are a lot more tough than paper, and they can be folded, creased repeatedly many times and then unfolded. That still is a challenge, though. The idea that after repeated creasings, even materials as tough as polyimides can degrade and crack. So that always presents a challenge for us.
Wonderful. And earlier we talked a little bit about how some of these structures get deployed into space. So Carol on Facebook wants to know, does the lack of gravity in space impact the designs? And do you face any challenges with the origami structure and deployment?
Oh yes, that is one of the sort of the most ubiquitous challenges when it comes to designing these kinds of structures, is that we have to test them on the ground. We have to make sure that they unfold correctly while they're still on the ground to make sure that they will unfold in space. But testing these kinds of structures on the ground has the side effect of there being Earth gravity on the ground. And we can't exactly flip a switch and turn that off. So how do we meaningfully test the unfolding of these structures in an Earth gravity environment when their operational environment has no gravity? So we have to engineer ways of doing what we call gravity offload or gravity compensation, where these structures are either strung up with strings and counterweights, or they're resting on air bearings on very flat tables, or they are resting on sprung supports to counteract the weight of the structure. And this idea and this challenge of gravity offload has been solved many different ways, and each structure sort of brings with it its unique challenges in terms of gravity offload. And then what that means is we have to not only design the structure to function in the environment of space, but also in a gravity offloaded Earth environment. And that brings with it its own challenges. It's a really fun, challenging set of issues or set of challenges that we have to deal with.
Very cool. We'll bring Manan back in a little bit for more questions, but our next speaker is a creative technologist in the studio at NASA's Jet Propulsion Laboratory. She holds a BFA in illustration, entertainment, art, designing vehicles, props, and environments for feature film animation from Art Center College of Design. She uses design thinking methods and techniques to imagine the future of technology in space. She earned her MS with the MIT Media Lab, focusing on space technology development, and works on creative projects and tech demos for various space missions. She is one of those people reminding us that we can always dream bigger. Please welcome Lizbeth De La Tour. Hi, Liz.
Hello. Hi there. Thanks, Brian, for having me.
Of course. Let's talk about some of your inspirations, some of what you called informal robotics.
Yeah, absolutely. So similar to London, this happened for me during my graduate studies at MIT. I was fortunate enough to be able to take a course at Harvard's Graduate School of Design, which is just down the road from MIT. And it was a course taught by Chuck Hoberman, who's a wonderful engineering designer. And it was really about rapid prototyping of robotics, taking paper very raw materials, and quickly creating prototypes that move and that can walk, swim, fly, those sorts of things. And so I was really inspired in that way. It was a lot of origami techniques within this course. And I was really inspired about taking the complex movements of animals, the biomechanics that animals use to walk and crawl, and translating those through origami. So you can imagine a flat-packed robot that can then pop up and walk around, maybe inspired by a mollusk or by a butterfly, and those sorts of things.
Well, speaking of butterfly, let's actually go to our next image, because you're a creative designer, and something you've talked to me about is simplification.
Yes, absolutely. So as a designer, we were taught to simplify everything, and that includes, for me, going into paper and simplifying those complex movements of animals. This is just a really rough example of how you might go from something flat in paper to something that moves. And always, when considering these animal-inspired robots, it's always important to remember, too, that animals come with stories attached to them, and we sometimes attach stories to the robots that we create as well, and a lot of cultural significance for certain animals. For me, my family's Mexican-American, and so butterflies have special meanings for us, but translating that and creating that movement here, actually, if you go to the next slide, we can kind of see it, how that might move. And so all of those, what Manan was talking about, the flat folding, those flat folds can then become engineered linkages that can, you attach a motor to it or an actuator, and they will move however you would like them to move. And it's great because it's very predictable. Mathematically, you can predict exactly how something will move. And I think that was really valuable.
Well, something you talked to me, you mentioned a mollusk before. And when I look at a mollusk, that's not immediately the first thing I think of for, make a spacecraft out of that. If we go to our next image, talk to me a little bit about this with these folds.
Yeah, so this was a project done at MIT with Gianni Zhang and Elena Kodama, and really it's actually exactly the same paper fold that Manan was sharing earlier with the four-wheeled robot that can flat fold. This is the Mira fold, and we used this, actually we studied mollusks for quite a while, so the movements of snails, snails that you might think are actually very simple, but they're actually very high-tech. They move in very special ways, and to recreate those movements actually was quite a feat. But with the Mira fold, we were able to create the motion of the mollusk and how it pulls itself along the ground using a lot of traction and actually padded feet. And so we created this very fast paper robot that can do the same thing or a similar thing. And yeah, and actually, I think if you go to the next slide, I can also share what the assembly looks like as well. Yeah, and so actually, so what we did, it's a very fast technique where we pre-etched the mountain and valley folds. So all of those folds are actually, it's a combination of hand folding and also mechanics. So we attached an actuator to it, we 3D printed the spine, and kind of put it all together. So it was actually very both art and science combined into one, which is really very nice.
Very cool. As I asked Manan, and I'll ask you, why is this specific style important?
Yeah, and so actually, we go to many different planets, and we explore many different environments, and I find that nature has solved a lot of the problems that we're facing already. And so being able to translate those complex movements through origami is actually very useful for exploration of terrains that we might not have thought of going to before.
Very cool. So what's next in biomimicry?
Yeah, so a lot of researchers looking into embedded electronics. How do we, specifically with folding of polymers, just looking at how are you able to embed electronics directly into the folds, because sometimes you need a shell or some kind of body to house the electronics. And so right now it is definitely a lot of looking at how can we create maybe just a flat sheet that can walk around and those sorts of things. So yeah, I think that's
very
next.
Cool. That's what's next. And speaking of what's next, let's bring Talia back in, who's been watching the chat, and see if there are any more questions.
Yeah, so we have a lot of great questions. Andres Jose on LinkedIn wants to know, how much more vulnerable do these electronic components become when you begin folding them in?
Oh.
That's a great question. Actually, so it really depends on the robot. So in this case, the robot on the screen here has a shell similar to a mollusk. And actually, that was very useful. So sometimes there is a housing or encasing that will protect them very well. So far, once you do start embedding a circuitry right into the folds, there is kind of some tension when you start folding, and that the copper of the circuitry starts to kind of fold along with it. And there's some tension there.
Great. So Anne on LinkedIn wants to know, does the requirement for folding these spacecrafts increase the likelihood that they'll fail in space?
I think I can answer that one. Ideally, we will have designed it very well on the ground before it goes into space. We will have already accounted for all of any failures that might happen in space. So I think they're very well prepared.
Very cool. We're going to bring Manan back in now. This topic, and both of you, your experiences are a great reminder of how important STEAM is. Not just STEM, but having a broad, wide-ranging education. What are some of the unexpected influences, things that you didn't think would influence you, but turned out to be hugely important for this type of work?
Yeah, so I can go first if that's okay.
Yeah.
Yeah, one of the things that has served as a sort of an unusual point of inspiration for me in the past couple of years actually has been the species of flower called the datura that is actually native to Southern California where we are, and it kind of just grows wild here. But the thing that struck me really was the way in which the surface of the flower wraps up. As you can see, the bloom has that amazing white surface fully unfolded. But when it's coming out of its bud, it is wrapped up in that very intricate sort of spiral format. And while it's unwrapping, while it's blooming, in that third image that you see, it kind of maintains its stiffness. It kind of has a stable shape to it because of this non-planar, out of plane sort of curvy behavior, the curvy form that it has. And that was partially an inspiration for designing that carbon fiber wrapped solar array prototype that we saw a video of, where when it was unfolded, it also had that sort of unfolded, curvy, sort of crenulated character that gave it some stiffness and stability. So, something as simple as a blooming flower can be really can be inspiration for these kinds of structures.
Very cool. And Liz?
Yeah, absolutely. And I'll actually go back to the mollusk and talk a little bit more about mollusks. That was a really unexpected inspiration for me in graduate school. And I'll say that because, we walk by mollusks and snails every single day, on a sidewalk. And we just imagine that they're very simple creatures, but they're really complex, and it's actually, it has sensory feedback, right? Its little eyes there, and a mechanical motion that happens because of that sensory feedback. And so just recognizing for me that something very simple is actually, it was very hard to do. It was actually a very big inspiration for me.
Wonderful. We're going to open it back up for questions for both of you now. So, Talia, how's it going out there?
Yeah, so we still have a lot of great questions coming in. Tom on LinkedIn, though, wants to know how much more cost-effective are origami designs? Why are we doing origami designs instead of just sending up the entire spacecraft?
It's not so much a function of cost effectiveness versus, just being able to fit a larger solar array or a larger antenna or a larger solar sail in a spacecraft platform which could not previously have fit that size of a structure. So it's more about enhancing capability and creating opportunities for these spacecraft to have capabilities that they could not previously have had, given the volume constraints that they have to deal with.
Great. So Abby on Twitter wants to know, what are some of the more ambitious projects using folding techniques and origami that have been suggested?
So one thing I'm going to point to is the James Webb Space Telescope, which is due to launch sometime this year. And this is an incredibly beautiful space telescope that's going to unfold not only its primary mirror, which has two folds within it that helps the mirror be larger than the size of the fairing the mirror goes in, but it also unfolds out this tennis court sized sun shield that protects the mirror from the heat of the sun, and that's a remarkable project that is currently underway. That I think uses these kinds of folding techniques in an amazing way.
Wonderful. So speaking of unfolding the Webb Space Telescope in space, Nate from LinkedIn asks, what kind of systems are used to unfold these designs?
It really depends on the application. Liz, if you can take a stab at, kind of the robotic implications of this afterwards. But in the case of, deploying these large structures, the motive force is sometimes a motor that is reeling in cables somewhere, or it's perhaps energy that is stored within the folded structure itself, where there is strain energy that is elastically stored within the structure that helps the structure unfold when it gets there. And oftentimes there is a secondary deployable structure, like a deployable mast or a deployable boom that unfolds out these large structures. But I know in robotics, for instance, different motive forces are used.
Yeah, absolutely. And in robotics, I like to imagine it as sometimes like opening a pop-up book in some way, and your hand is the motor, and you pull, and a motion happens. At least in my brain, that's always how it has worked. So when you think of a limb moving or an appendage moving, there's always that motor that is making that happen. And the actuator, it can be many different things. Some people use pneumatic actuation, or standard, just regular old actuation with a motor. And and so that's usually it's kind of housed and encased somewhere within the body of the robot.
Great. So when we're doing origami at home, we're usually like making a butterfly or making a crane, and those are usually really, really delicate objects, right? So Krishnam on YouTube asks a really great question. How do these really delicate designs withstand a rocket launch?
Yeah, that is another one of those sort of quintessential challenges of designing these kinds of structures, and the answer ends up being, um, uh, using engineering principles and engineering design methods and techniques to make sure that the materials you use and the way you engineer them are able to withstand those launch forces. So typically, one does not use delicate things like paper. We use things like carbon fiber composite materials, or metals, or glass fiber composite materials to engineer these kinds of structures. And then, obviously, before they get even close to a rocket, there is tons and tons of analysis and work that goes and testing that goes into making sure that when these structures are within the rocket being subject to that incredible amount of vibration and acoustic noise, that these structures will survive. So there's an incredible amount of analysis and engineering and testing that that goes into the design of these structures. But from a fundamental standpoint, it's about using the correct materials in the correct ways to make sure they can withstand these forces.
Great. So you talked a little bit about, having to make sure that these materials withstand forces, but apart from that, Kier on LinkedIn wants to know, what are some other current limitations that exist for designing foldable spacecrafts?
That's a really good question. Liz, do you want to take that?
Yeah, I can talk a little bit. So, of course, there's always the embedding of the electronics within the folds. That's something that has been a really big challenge for a while. And yeah, also even materials are always a challenge, right? Lots of testing goes into them, but really it depends on a lot of the environment that you'll be going to. And like for example, if you go to Venus, you need to coat it in Teflon because it's very acidic in those clouds. So I'm just thinking along those lines of there's both kind of the stability of launching, and then also once you get there, what happens to it. So yeah, a lot of different problems in many different ways.
And from a large structures.
Oh, sorry, go ahead.
Sorry, I was just saying, from a large structure standpoint, it's the challenges that face this community have to do with how do we make things bigger, because in many cases bigger is better. Bigger solar arrays are better and bigger apertures are better. How do we pack them into our spacecraft and into our fairings even more tightly? And how do we keep mass low? Because obviously every pound launched is cost. That costs a certain amount of money. So you end up with these structures that are very large and very thin, and that ends up creating design and engineering challenges in its own right when you're having to deal with these. In the case of, say, solar sails, you're dealing with membranes that are so incredibly thin that it becomes a challenge to package them and to test them. We're talking about membranes that are as thin as a few microns, which is about 1/100th the width of a human hair. So these are incredibly gossamer structures that we need to think about engineering and designing.
Very cool. We've got time for one more question. Yeah.
All right. So for both of you, Tim on YouTube wants to know, what's a lesson that you learned in school that still makes an impact in your work as creative technologists and just creatives?
Oh, I can take that one really fast. Yeah, and so I think that sometimes there are some mechanical movements that just a robot just won't walk, no matter how much you want it to, and no matter how much it looks like that fold will walk. And so I think a big lesson for me was learning how to move on from a design, or how to improve it, or know when to move on to the next step. I think that was a big thing for me.
I really have to go back to my first class in civil engineering that I took, and my professor told me 3 rules that have always stuck with me. that are the most important for structural engineers like myself. The first one is F equals ma. The second one is you can't push on a rope. And the third one is to find the answer, you must know the answer. Yeah.
Those are all great tips to walk away with. That's all the time we have for questions. But before we go, I did want to get just from both of you one final thought. What is, besides those wonderful tips you both just gave us, what is the one thing you'd like your audience to walk away with today? Let's start with Liz.
So I think the biggest takeaway for me would be art and science are more similar than you might think they are. You might find inspiration for engineering in the DIY section of a bookstore. You can start, what's great about origami is you can start working on it today at home with a piece of paper and just start folding. And
Very cool. And Manan?
Yeah, kind of echoing what Liz said. One doesn't typically think about origami when one thinks about engineering or science or math. There's all these ideas in people's heads about science, engineering, and math as this one thing and one thing alone. But I think it's been fun for me to realize over the course of my work that there are many entryways. There are many different ways you can approach science, engineering, and mathematics. And origami is one of those unexpected but wonderful ways where we find that something as tactile and as wonderful as origami has applications in engineering, and that's just a wonderful thing to realize.
Very cool. That is all the time we have for tonight. Please join us next month. We'll be discussing planetary protection with Dr. Mujige Cooper. I'd like to thank our speakers tonight, Liz De La Torre and Manan Arya, for their expertise, their kindness, and their joy. A reminder also that you can't push on a rope. Thank you to Talia and everyone behind the scenes that make these talks possible. And a big thank you to all of you who join us every single month. Please stay safe, stay kind, and we'll see you in February.
It has been called the world's greatest piggyback ride, a space shuttle atop a Boeing 747 jet aircraft. But this is no ordinary 747. This is the Shuttle Carrier Aircraft, the SCA. This specially modified jumbo jet was not only a taxi service for the shuttle, but also helped in the development of the shuttle itself. In 30 years of flying, the majestic image of a spacecraft joined to the SCA became a symbol of American invention and ingenuity. You searched the sky. You heard the roar of the engines getting closer. Then someone would shout, "There it is, the SCA." In the 30-year history of the space shuttle, if you were one of millions of people who saw the SCA fly over your town, you understood the excitement it could generate.
And so it was always a pleasure to have the locals come out and have the kids be able to look up and see a shuttle sitting on top of an airplane. That's certainly a huge memory of mine. When I was a teenager, when I lived in Huntsville, Alabama, where I was raised, and at the time I was at Von Braun Civic Center in Huntsville and looking up and seeing this airplane, and who would have thought that I would have ever flown this airplane? I mean, how ironic that I would end up being a guy who flew the airplane and being lucky enough to be the last guy to fly this vehicle for a 30-year shuttle program.
The unique image of two sleek vehicles attached in a seemingly impossible configuration evokes feelings of progress, elegance, and achievement. To understand how the shuttle carrier aircraft came to be, you must understand the shuttle itself. It was America's first reusable spacecraft. At the end of a space mission, the shuttle would re-enter Earth's atmosphere. Then it would glide down to a runway at the Kennedy Space Center in Florida. There, engineers would get to work refitting the spacecraft for another mission. But NASA had other landing sites, such as Edwards Air Force Base in California. If the shuttle landed here, it would need a way back to its launch site in Florida. For flying the skies on Earth, NASA engineers first thought that perhaps the shuttle could have its own jet engines. But these proved to be too heavy, too complex, and too costly to develop. NASA would have to find another way to transport the shuttle. Enter John Kiker, an engineer at the NASA Johnson Space Center in Houston, Texas.
I made a little sketch of this and put it on my desk, and then after several weeks I called up Owen one day and told him not to laugh, but I wanted to show him something.
Using model airplanes, Kiker and his team proved the concept of transporting the shuttle on the back of a 747 jumbo jet. In addition, the tests showed the shuttle could be air-launched off the back of the plane. The idea was accepted, and the shuttle carrier aircraft was born. The SCA first flew the shuttle on what was called the approach and landing tests. The shuttle Enterprise was lifted on the back of the SCA to an altitude of about 27,000 feet and air-launched. The aerodynamic tests were crucial in proving the shuttle's ability to glide down to a landing and helped engineers refine the shuttle design. Just as significant, the imagery of the SCA and shuttle in action was the public's first glimpse of an amazing new era of spaceflight that was just on the horizon. The shuttle became a renowned and iconic space vehicle. The SCA allowed those of us on the Earth to share that excitement when it served its role as a shuttle taxi. Mission by mission, SCA crews eagerly listened for word if the shuttle would have to land somewhere other than Florida.
We start getting excited when we hear that the weather is bad in Florida. Those few of us that fly this airplane like bad weather in Florida. So we get a chance to do our job. So as soon as we know that the shuttle is en route to California, that's when we start getting involved with the shuttle ferry team. So basically the shuttles are brought into the demate facility, and they're hoisted up, and the shuttle carrier aircraft, the 747, is moved under the shuttle, and then the attachments are made.
The shuttle and its cargo can weigh anywhere from 160,000 to 220,000 pounds. To lift and fly with that much weight on its back, the SCA had some special modifications that made it unlike any other jetliner. Most noticeable were vertical fins mounted on the tail. The shuttle caused air turbulence, and the fins brought back stability to the flight. Other than the fins, it might appear this was an ordinary jumbo jet. But as SCA flight engineer Henry Taylor can tell you, there were some very important differences between a regular 747 and a shuttle carrier aircraft.
We're here inside the main cabin of the shuttle carrier aircraft. As you can see, there's no insulation, no paneling. All the lavatories and galleys have been removed to save weight. Above me is one of the two bulkheads, this one and this one, that are used to provide support for the orbiter attach points. The attach points for the shuttle carrier aircraft are in the same location that the orbiter is attached to the external tank for launch. The aft section of the airplane, there's two struts with what we call balls, and those go up inside the orbiter. In the front, there's a small little tripod adapter fitting that mounts to the structure that's been added to the shuttle carrier aircraft. Somebody made kind of a joke, although it's relevant. By the aft attach points, it says attach orbiter here, note black side down, which of course the black for the tile, so it's kind of a joke, make sure somebody doesn't put it on upside down.
Although the plane itself had all the necessary technical requirements for a safe flight, the highly skilled crew monitored the systems carefully and experienced a different type of ride.
From a pilot standpoint, there's a long wait. When the power's pushed up, you don't really realize the time that you're going to be on the runway before rotating the airplane into the air. So there's a big wait, and that's the big thing that was impressed upon me, I think, during my first shuttle fair.
As the shuttle program ended, the SCA had one final mission: deliver the shuttles Enterprise, Discovery, and Endeavour to their respective museums. Across the United States, for one last time, people got to see the unique vision of spacecraft and aircraft joined in flight. And with that, the SCA with the shuttle was not seen in the sky again. But it will always remind us of a bold age of determination and invention.
When the orbiter is on top of the SCA, it just creates so much interest because it's such a unique site that people come out by the thousands to see us wherever we stop, to come see this very unique combination. People appreciate and people respond to things like that, the American ingenuity and American pride.
Orion is getting ready to launch. My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right: fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. We are headed 3,600 miles above Earth. 15 times higher from the planet than the International Space Station. As As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home. The upper stage of the rocket triggers separation. Orion's jets fire to turn it into the proper position to re-enter Earth's atmosphere. No matter what happens now, we're coming in. 75 miles above Earth, the spacecraft enters the atmosphere. Things happen quickly. We're now traveling more than 20,000 miles per hour. Air particles pushed out of the way heat up. An envelope of hot plasma surrounds the vehicle as it plummets towards Earth. The plasma reaches temperatures of 4,000 degrees Fahrenheit, almost twice as hot as molten lava. This may be the most dangerous part of the flight. Mission Control is monitoring all the data from the spacecraft, and then we lose communication again. No data can penetrate the plasma. Orion is on its own. Orion is inside a fireball. Onboard systems ignite jets to keep the ship pointed correctly, so the specially constructed heat shield takes the full brunt of the inferno. This is the largest heat shield of its kind ever made. Orion's computers command the spacecraft to bank like an airplane, keeping a precise path to the landing site. Even though we've slowed from 20,000 miles per hour to about 300 miles per hour, we're still traveling amazingly fast. We must slow down to safely land in the ocean. Luckily, we have parachutes. Specially designed for Orion, the parachute